So what we've just done is some experiments. We've mixed some chemicals together and looked at temperature changes. What I noticed when I walked around the room is that different groups had different temperature changes. But we got one thing in common. The experiments that got hotter for all of us. The temperatures, the ones that got colder for all of us. When we measure energy change, we need to measure it against something that is standard. So we need to have a standard unit and a standard way to measure this. So what we do is we have a thing called enthalpy, which is not temperature. Temperature is part of it because temperature is a measure of the average kinetic energy of the particles in a substance. But it's also a measure of the energy found in the chemical bonds. So it's a combination of things. So if you sort of think of it, you might have heard the term chemical potential energy. It's kind of similar to that. It's not the same, but it's similar to that. Because we've got this thing called enthalpy, we also need to have a unit that is standard. We also have to have a unit that is standard. Now, you guys are all using different volumes and different amounts. You actually had a teaspoon or a spatula full or whatever. That wasn't a measure that we can actually use with any reliability. So what we do instead is we talk about it being per mole. And a mole is an amount of substance. The actual value for it's not important, but 1 mole is 6 times 10 to the power of 23 particles. So it's a massive number. Because in chemistry, we really are talking about massive numbers of particles reacting. So what we do is we measure it per mole of substance. So we'd actually measure the mass of it or the volume and work out how much in moles we've actually got to be able to do some calculations. We're going to do some of that later in the topic, so I won't spend any time on that now. And the other part of the unit for enthalpy links to the fact that it's to do with energy. So it's in kilojoules. Okay, now I know physicists use joules as the SI unit for energy, but at chemists we use kilojoules per mole for enthalpy. So we're looking at kilojoules. They're just a bit more of a meaningful number for us for what we're looking at to link to temperature change. Another key thing to look at here is we notice things got hotter or colder. That's the environment that's getting hotter or colder. These reactions do not create energy or destroy energy in doing this. What they do is they transfer or transform it. This is a physics principle called the conservation of energy. So the energy has to have come from somewhere if it got hotter, or it has to be being absorbed by something if it's getting colder. And so what we do is we use the words exothermic and endothermic to explain what we observe. Exo meaning outside, so it gives off energy, it releases energy, which means we'd feel it getting hotter. An exothermic reaction feels hotter to us. What it means for the particles is quite the opposite. The particles go from having a higher energy value to a lower, enthalpy value to a lower enthalpy value. Endothermic things feel cold. They're absorbing heat energy from their surroundings, from your hand, from the air, from water, from wherever. And they go from the chemicals having quite a low enthalpy to having a higher enthalpy. When we look at this next year, you'll go to another step where we look at a thing called entropy, which is the disorder of something, to explain why something would go from having a lower energy to a higher energy, because it seems counterintuitive. Why would something do that? Why would it be more stable if it's requiring more energy to hold it together, basically? So I'm going to use 2 of the examples that we had in our experiment to show you how we show these on a graph, but also to explain why they got hotter or colder. So one of the ones we did was we had hydrochloric acid and sodium hydroxide. After they reacted, most of us noticed that it got hotter. So it meant that they had to release some energy. The products, so sodium chloride and water, have a lower enthalpy. The kinetic energy would be about the same because the temperature change wasn't huge. So the kinetic energy is about the same. So it means that that must be in the bonds. The sodium and chloride attraction must require less energy to hold it together than the hydrogen and chloride and the sodium and hydroxides. Same thing for the water. It must require less energy to hold it together, or enthalpy, I should say. So at the end of the reaction, the products would have an enthalpy down here somewhere. So we end up with an enthalpy change. And our enthalpy change has gone from here down to here. So on a graph, when something goes down, would it be a positive or a negative value? Negative. So what we say here is our delta H, enthalpy change, is negative. Now we do have actual values for this. If we had worked out the exact volumes and the concentrations of everything, we could actually mathematically work out exactly what that value was for our reaction from temperature change. We didn't do that. This was just a bit of bucket chemistry. But we've got a negative enthalpy change. Well, in that case, why don't these two chemicals just automatically react every time they come near each other? Why don't they just automatically react? Because they don't. There's a rate of reaction here. What is required before anything can react? Let's try to go to last year.
Is that activation energy or something?
It is called activation energy. You need to break some bonds. The collisions have to occur in such a way that the bonds will break to allow new bonds to form. So what happens is, when we mix these two chemicals together, you probably stirred them a bit, or the energy that was in the water that they're dissolved in allowed it to increase the actual overall enthalpy value just a little bit, enough for them to react. And then it very dramatically drops down there. As was just said correctly then, this value that it goes up to is called the activation energy. I'm pretty sure I'm higher, so it's not. And it's a particular kilojoules per mole again. Activation energy. This activation energy idea is going to be really important in this topic to explain why reactions don't happen spontaneously all the time. But also it's really important in another topic we're going to do where you talk about rates of reactions. Because you have to have, the more particles that have this activation energy value, then the more likely a successful collision or reaction is. But in this topic we're just aware that it's a certain value on the graph, a certain number on the graph that the particles need to get to in order to react. So to make the collisions energetic enough to be a reaction. Notice that the enthalpy change isn't from this top point, but it's from this point here. Okay, so it goes to this point here, not from this point here. It's negative, which is our important thing for exothermic. Okay. That was a good example. You'll often be asked about physical changes as well, because they can be described as exothermic or endothermic. Anything where it goes from something at a high enthalpy to a low enthalpy is going to be exothermic. So for example, condensation, where I've got gaseous water and it turns into liquid water. Now those, the bonds are pretty much the same. The chemical bonding is about the same in those. There's no H and O bonds being broken there. But what's changing when you go from a gas to a liquid? Looking at our enthalpy definition. Kinetic energy. Okay, the particles are slowing down. That energy has to go somewhere. It can't be created or destroyed. In this case, destroyed. It has to go somewhere so it gets released as heat energy. Okay, so when we actually cool something down, we're removing that heat energy from it so that it can change state. Okay. Conversely, therefore, evaporation would be endothermic. You need to pump energy into it to make it occur. Right? You need to find a heat source to make it occur. So that leads me to the next one. We had these two solids mixed together. Now the giveaway that this was endothermic for me was that it started off as two solids, and what did it end up as? Sort of went a bit slushy, didn't it? So it turned into a liquid. So if you got it nicely mixed, it would have gone a little bit slushy, okay, almost like a semi-liquid. So the products that it made must have had a higher enthalpy because it went from solid to liquid. So that sort of makes sense. So the particles got more kinetic energy. As well as that, you've also got the bonds that are being formed in the products have got more enthalpy, more chemical energy between them as well. Again though, if we'd done this on a cold day, you might have observed nothing, because it actually required a bit of energy from the surroundings to kickstart the chemical reaction. What do we call that little bit of energy that's required to kickstart it?
Activation energy.
Perfect. Okay, so again, there's a value up here that has to get to. And then when the bonds are formed in the products, it drops it back down to this new enthalpy value. So again, oops. I've got my activation energy there. Now, where do we think the enthalpy change goes to? Does it go from there to there, there to there, or there to there? Which one? Second one. So if I extend that one out, we're saying that it's going just there.
Yeah.
Cool. Okay. And we notice that whereas that one's negative, this one's going up in a graph, which means the value is going to, the difference is going to be positive. It's going to be a big number minus a little number. Another change of state example, like what we've got there, would be if we started with liquid water and we boil it. And understanding that activation energy will also help us understand why you don't get to the boiling point for water to evaporate. Yep.
Could you make an endothermic reaction without increasing the temperature just by moving the particle or the?
I suppose in theory you could, but once you move the particles more, you are increasing the temperature by default, because that's what it is. An increase in kinetic energy is an increase in temperature. Okay, so. But yes, in theory there'd be other ways, and I suppose you could do it by adding electricity, for example, which wouldn't change the temperature, but would allow for the reaction to occur. If you provide energy, something could happen, whatever form that energy takes. Okay, so in a nutshell, what I want you to get out of today is there is this thing called enthalpy. It's kind of like energy, but there's a bit more to it. Okay, because it's not just chemical energy, it's not just temperature, so heat energy, it's kind of everything put together. Energy can't be created or destroyed, so if I observe a temperature change, that means that energy is being transferred or transformed. Okay, so it's being turned from one type into another, probably from chemical potential energy in the bonds into heat energy. That means the enthalpy of the products is different to the enthalpy of the reactants. If that change in enthalpy is negative, we call it exothermic, and it should feel like it gets hotter. Exo, outside, thermic energy or heat, so it gives off heat. If that enthalpy change is positive, it's what we call endothermic, and endo means inside, so it takes in heat energy. Okay. The other thing to take out of it is that our unit is the kilojoule per mole, so we're always trying to measure it against 1 mole of substance. So when we do balanced equations for this, which we'll get to later, we're always trying to get 1 mole of whatever's being reacted to be our thing we measure it against. Any questions before I stop that? Okay.